the equipment problem, replacement problem. So if we can read the problem statement first. So this is a second problem that is a business problem, but we're going to translate it into a network problem. Okay. Okay, so what's this problem is about? Let's read it together. The company owner is trying to decide between two different contracts. And this contract is about how to keep this this equipment, to obtain the equipment and then keep it for how many years? Guys, you guys read the problem statement. Did it say?
5 years.
Okay. To decide how to carry this new equipment by replace it. And so this person can use it for 5 years, right? Okay. And so these two contracts both require him to pay this initial cost to buy this new equipment, okay? And then in the two different contracts, let's just look at the first contract. The price to acquire a new equipment will increase by 6% per year. Okay. But he would be given a trading credit for 60% for any equipment that is 1 year old. Okay. So this means that now he buys a new equipment, and if he decides to trade in this equipment after 1 year, the price will increase by 6%, but he also gets 60% of what he paid initially. Okay. Or he can trade in after 2 years, and he gets 15% for the 2 years old equipment. Okay, so that's the first contract. And under the second contract, the difference is just the rate at which the equipment price increases. Okay, and also the percentage of credits he gets for the trade-in. Okay, then he needs to decide which contract to use. But if you look at under each contract, for example, for the first contract, do you know how to trade in? There are different options, right? He can trade in after 1 year every time, and another one after 1 year, 1 year, 1 year, 1 year. Okay, for 5 years. So he will trade in 4 times. Okay, or he can trade in after 2 years, and 2 years, and 1 year for the 5 years plan. Okay, or he can trade in a 1 year, a 2 year, a 1 year, and another 1 year. And another 2 year. So just to carry from the beginning to the end of the 5 year, there are so many different ways to go, right? So what does that mean? What's his first decision? Before he can decide which contract to use, he needs to figure out, okay, under each contract, what's the best way to go, right? Okay, so let's go to some general information. Okay, so and from the problem statement, you see that under each contract, you can trade in only at the most like 2 years old equipment. Okay. So it does not provide any info on, say, okay, what if you're trading after 3 years? So that means it's not possible. So you can only trading after using it for 1 year or 2 years. Okay, and so this is what we analyzed. Okay, so you have to trading at least every 2 years, and the initial costs are the same under both contracts. Okay. So these are the two different contracts, and we just talk about the price increase rate different, the trading for 1 year, 2 year old, these are different. Okay, so the first thing we want to do is to figure out, okay, under each contract, what's the optimal way to go? And once we find out optimal way to go, we compare the optimal of both, and then we decide which contract to go. Okay, so, and what's the goal? Sorry, I forgot to ask that. What's the goal? What's the objective? Minimize the cost, right? Okay, so he wants to find the minimum of the minimum costs of both contracts. Okay, so let's see. So we are going to So just now I asked what's the planning time frame. It's 5 years. Okay, so let's just look at the first contract. So let's think about it in this way. So here, we're in year 1, and we have to go to year 5. Okay, and from the analysis, we already hinted on it. There are multiple paths to go. Okay, we can go say, okay, 1 to 2 years, 3 years, 4 years, and 5 years. So that's one way to go. That's the first option I said. You just trading after every year. Okay, or you can go trading after 1 year, and then trading after 2 years from 2 to 4, and then trading 1 year to 5. Or you can do 2 years here, and and then another 2 years here. Or you can do 2 years here, 1 year here, and 1 year here. So there are just different ways to go there. Okay, and once we have this figured out, and they are all those arcs have directions. Okay, once we figure out this, okay, we say, oh, does this look similar? This is it's a path network, right? And we're thinking about, okay, we start with one equipment, and we want to carry this equipment by trading it in different ways all the way to here. Okay, so it's kind of like we have a -1 supply, which is just one supply here. We have this one computer that we're going to buy at this cost initially. And eventually, at the end of 5 years, we still have this one equipment. Okay, and those nodes here just represent the years. And the arcs here represent the different ways of trading. Okay, so let me change the color. Okay, so let me change the color here. So these black arcs represent a 2 years trading, okay, and those red ones represent 1 year trading. Okay, so with this initial analysis, we find, okay, we can transform this problem into a network, okay, and by thinking it in the way of a shortest path problem. So do you guys remember what's the objective in the shortest path problem? On the from the shortest path problem on each of those arcs here, we have a distance, right? Okay, and then we're trying to minimize the total distance from starting point to the destination point. Okay, and then we do that by minimizing the total sum product of all the xij. Xij eventually will turn out to be binary variables 1 or 0, being selected path or not. Okay, and in this problem, we need to figure out the cost on each of those arcs. In the shortest path problem, those ones are given. We already know, okay, so from 1 to 2, how many miles or how many hours to go? From 2 to 4, how many hours? But in this problem, we don't know. Okay, so that's something we have to figure out. That is the cost to go on each of those arcs. Okay, so first let's use what we have. Okay, so initially we require 60, so I'll put it here, 62K. So let's see, our objective is to minimize the cost. So I'll put the cost as a positive value. Okay, so here, initially we'll have this cost will occur. Okay, and if we trade in the second year, what happens when you trade in? You have to pay, right? You get a trading credit, but you have to pay for the new equipment. And we said the contract, the price will increase 6% per year. Okay, so that means here, when you get to here, you will have to, I'll put here, 1.06% times this. So that's the cost that will occur at this point here. Let's just look at the 1 year trading for now. Okay, so 1, 2, 3. And when you go to year 3, the cost change again. Square, right? Times 62K. And when you go to the 4th year, to the 3rd, okay, and when you go to the 5th year, 4th. These are all the costs that will occur when you trading at those different years. But we also said you will get a trading in value, and we're considering just the 1 year trading right now. You get 60% out from what you paid for it. Okay, so that's one thing to be careful. This 60% is what you paid for. Okay, so for example, when you're trading on this path, you get, so we'll use negative value, okay, because what we write here is a cost. So negative 60% times what you paid for. So it need to be this value, because when you purchase this equipment, it's 62K, okay. Then if you go here, this path means that you are trading, so you're already trading, you get the new equipment, okay, here. And then you are trading after 1 year again. And so that's 60% times whatever you paid for at this point. Okay, so remember why I use this value is because it's already, you are already considering new equipment that you acquired at this point. So it should be this value here times 62K. Okay. And if we keep going, okay, so this person is going to trading again after 1 year. So at this is 3 year. At the beginning of 3 years, this person already trading, get a new equipment that costs this much value, and he's going to trading again. So that's 60% times this value here now, okay? Percent raised to square times 62K. Now, I'll ask someone. So what's the trading value when this person trading again in the 5th year? Times cube, okay, times, because when we're trading here, we're considering the equipment that we purchased here, right? Okay. And all of these ones need to be negative value, negative cost, okay, because we want to minimize cost. So these are the, for 1 year trading, okay. And then those black arcs we created represent 2 year trading, okay. So what's saying that, okay, for this new equipment that we purchased at 62,000 at the beginning of year 1. We're going to use it for 2 years, and then at the beginning of year 3, we're going to trade it in. Okay, we already put the price here, the price at the cost that is going to occur when we buy the new equipment. But here we'll have a trading value. And remember now this is a 2 year trading, so we only get 15% back. Okay, so here 15% times whatever amount we paid for it. Okay, so it should be this 62K here. And look at the second one, the second 2 year trading. So, oh sorry, let's just keep doing this one. And if we're going this way, we're saying, okay, then after another 2 years here, at the beginning of 5th year, we're going to trading again the equipment that we purchased here. Again, we only get 15% back. Okay, so this way we're saying, okay, we're just trading 2 years and 2 years. Then if we go this way, for example, okay, a 1 year trading, a 2 year trading, and a 1 year trading. If we look at this one, what does this arc represent? This arc represents we're going to trade in the equipment that we purchased from year 2. Okay, does that make sense? Okay, so always remember that arc from, so the from node represents the year that we purchased the equipment, and the to node represent the year that we're going to trade in this equipment. Okay, for example, this arc represents we're going to trade in the equipment that we purchased at the beginning of year 2, now at the year 4. Okay, so and this is a 2-year trading, so we only get 15% back times what we paid for, and the equipment we paid for is from here. So it should be 1.06% times 62K. Okay, so now with this, I hope you now see why I put the equipment purchase cost on the node, and why the trading values on the arcs. It's because we have those different combinations that we can go. But whichever way we go, if you are going to go through a node, that means you are trading that year. Think about it again, okay? If we are going through whichever, say, okay, pick a node. Someone pick a node. So node 4, okay? What does that mean? No matter it's going from this way or this way, this node 4 here means, okay, we're going to trade in the product. Okay, we're going to trade in the product and we're going to buy one new. And that's why this occurred here. So this purchasing cost occurred here. And depending on which way it comes from, that equipment that we're trading, depends on whether it's this way it comes from or it's this way it comes from. The trade-in value, the percentage of the trading value, and the equipment cost depends. Okay, for example, if we're considering this way, we are now at the beginning of year 4. Whether it's going from here or going from here depends. Okay, if I come here, we'll say, okay, that means we're trading the equipment that we purchased from year 3 under a 1-year trading plan. So we get 60% from what we paid for that at that time. If it goes from this direction, then we're just saying we're trading this 2-year-old equipment that we purchased in year 2, and we only get 15% from it. Okay, so these are the costs. So now, with this analysis, what do we get? Which part do we get? Which part of the model can we get? The objective function, right? Right? Because we're trying to minimize the total cost, and so here we get the objective function's coefficients. Okay, so and let's put the decision variables first. We didn't talk about that, but because they are the same for all the network problems. Okay, so our decision variable will be xij represents, and we know that we're going to treat this as a shortest path problem. Okay, so it will be 0 or 1. Let me revise the order. Okay, so I'll put 1 or 0. 1 means choose to trade in equipment purchased in year I. I would say in year J. Choose to, if I write in this way. So read it to see if it makes sense, or if you have a better way to express this. So we're saying choose to trade in the equipment we purchased in year I, now in year J. So this year J means the trading year. Okay. This means otherwise. If we have a better way to write this decision variable definition, please share. Or you can put here, say, okay, equals 1 means in year J, choose to trade in the equipment that purchased in year I. Okay, so either way. And the 0 means otherwise. Okay, we know that because we're going to treat this as the shortest path problem, and for the shortest path problem, the decision variable values will just be 0 or 1s. Okay, because we have only one supply and one demand. With the constraints that follow the balance of flow rule, it's guaranteed that we will get integer solution. That means we'll get 0 or 1 for the decision variables. Okay, then we have the decision variables. Now we need the objective function. We said we're going to minimize the total cost. Okay, so go back here, minimize total cost. That means we need a coefficient for all the xij's and sub them together. So look at x1, 2. What's the cost?
Minus 60% to 62.
What's that again?
I mean, over the arc.
This one and this one, right?
Yep.
Should we consider this value here?
No, this is.
No. Okay, why?
This is supply. Initial investment.
Okay. Okay, so that's the initial investment. Okay. We don't consider this because it's the initial initial investment, and it's the same for both contracts. Okay, so we don't need to include this one. Okay, so then the cost that happens on this arc would be this value, subtract this value here, right? Okay, so go to the next slide. Okay, minimize 1.06% times the 62. I'll use K, $1,000 as the unit, so I won't write K here. Okay, subtract the 60% times 62 times x12. So this is the cost that's going to happen with this arc. Okay, plus then we look at x13. Okay, so for x13, what's the cost? So this value here, subtract this value, right? When you go to this node 3, so when you go through this arc, the cost that is going to occur will be this equipment purchasing cost, subtract the credit you get. Okay. Okay, so plus 1.06 square times 62. Subtract. This is a 2-year trading plan, so we only get 15% times your x13. Okay. Then go back. 1, 2, 1, 3, done. Then we'll do 2, 3. x23. So the cost that happens on this arc would be the equipment purchase cost, subtract this trading value here. Okay, I'll ask you guys to write it down, so you tell me when I go to the next page. Write down your own coefficient. What's that?
Tree is trading.
Every node represents trading.
So if it is trading minus purchase.
Right, right. The trading cost
1.0.
subtract the credit you get.
But if you're subtracting, so the negatives should change to positive, right? So we are adding these two together.
No, I put this as
Just to
the
show
negative
that
sign,
we are
right?
purchasing.
Because it's not a cost. Okay, you guys done? Can someone tell me? We're writing for x 2, 3, right? Okay, subtract
60%.
times what?
1.06
6. Okay,
times 62.
times 62. Okay. Okay, so with this, we can write all the rest. x2, 3 and x2, 4 plus, yeah, the 3, 4. So 2, 3, 2, 4, and 3, 4, 3, 5. 3, 4, 3, 5. And the last one would be x 4, 5. Okay, so I won't write all of those out here. You have this slide for your reference. So make sure it's the purchasing cost subtract the credit you get on the arc, on the inflow to that node. Okay. So you can see this problem, the difficult part is coming up with those coefficients which are not given as compared to the previous shortest path problem. Okay. So now, what are the constraints? For all the network problems, constraints are the same, right? You want to make sure that in this case, we have only one supply and one demand. It's a shortest path problem. So for all the nodes, the inflow minus outflow need to be, in this case, equals to the supply or demand. Okay, so for node 1, we don't have inflows minus outflow. We have a supply of 1 there. Okay, and then for node 2, inflow minus outflow can go to 2, 3, and can go to 2, 4. And all of these middle transshipment nodes, they have demand of 0. Then for node 3, one 3, right? 2, 3, minus 3, 4, 3, 5. For node 4, 2, 4, 3, 4, minus 4, 5 equals to be 0. Inflow, outflow. Okay, and then the last node would be node 5. So inflows minus outflow, no outflow, equals to be demand. Okay, then all xij need to be greater than or equal to 0. For all ij goes from 1 to 5. And that's the model for this problem for contract 1. Okay. Okay, so that's the model for contract 1. And what we're going to do is that for contract 2, we do the same thing. So we create this 1, 2, 3, 4, 5. This network for contract 1. And the difference would be the cost, the credit that happens on those arcs and the cost that happens on each of those nodes. Okay, and follow the same logic here we used. Just change those, the 6% now will be changed to what? 3%? Okay, and the 60% will be changed to like 30%, and this 15% will be changed to, 10%. Okay, and then you solve this second problem. You will find what's the optimal path under each contract. And then you compare those objective function value, the least one. Okay, so you will find that the complete solution would be, okay, if we have time, we'll implement this. The complete solution would be, okay, the suggestion is to select contract 2 and to trading the equipment every 1 year. So that would be the final conclusion. Okay, so you select the contract and also the optimal path to go under each contract. Okay, so this is a problem that we transformed to a network problem. And to start it, we look at the possible ways to go under each contract. And we used this number, 1, 2, 3, 4, 5, representing the beginning of the year. Okay. Analyzing this way help we build a model that's really simple. Okay, the only part that's complex is to figure out the costs that occur associated with each node and the arcs. But you can see that constraint is really simple because we translated it into a shortest path problem, and these are just the constraints that you use for all the shortest path problem. You don't have to add any other constraints. Okay. You can think about other ways to formulate this problem if not using a network problem. Actually, many of the problems you can formulate them in different ways. This one, we formulate in network problem because like the way we analyze it, we use those like to represent the different way to go. We use the paths, arcs. You can also maybe create this in a table format, but the logic will be much more complex. I actually had one student formulate this problem using integer LP, like the ILP, the integer linear programming, which we'll talk about at the end. That's chapter 6. So the logic is that, okay, if you're trading in the second year, so if you choose this one, then you have to go from this second year to 3, which means that if you're trading this year, you can't just start from 4 unless you're trading in 3 to 4. So there is some logic involved in that kind of modeling. So this problem, you can model it in a different way, but it's way too complex. Okay, you guys see what I'm saying? Like the logical, you have to make sure that, okay, if you start to trading in if you start to trading in the third year, then you have to make sure that you either traded it already in 1 to 3 or 2 to 3. If you model in a different way, but modeling it in this network problem format is much easier. We just figure out what's the cost that associated, and then we have this balance of flow rule, shortest path problem constraint. Then we're done. Okay. Okay, so this is the formulation of this equipment replacement problem, which is pretty important. Okay.